All right, cool. So let me go over the do now. I'm just going to go over these two molecules to the achieve level just to make sure you guys have gotten all the right things identified. And in fact, some of this will start going to the merit level. What I've given you guys today is an assessment requirement kind of checklist. This is basically exactly the same thing I am using when I am marking your assessments. Your assessment is more or less going to be 3 spectra and figure out the molecule for me. Sometimes I will give you a hint like the empirical formula. Sometimes I won't because the molecule is a little bit easier. So do kind of keep that in mind. So if I was to look through the checklist, the first thing that I need to do is I need to identify on the IR things that are there or things that are not there. So remember, the two things you're always going to use as your reference point is going to be your 1700 and your CH. So I'm just labeling those to help with my little navigation. And now what I'm trying to do is identify things that are there or are not there. So I've identified that this one has an OH. This one has no C double bond O. So when it comes to the achieved, I only need one thing identified. I don't need all of it. So long as you get the OH or the no carbonyl, I would have given you an achieved for that one. If you got both of them, so this is my and you're stating that you now know that this is an alcohol, you're working up towards the merit level. Are we good so far? All right, I'll also look at molecule number 2 just so that way you guys can see them both in parallel. So what I said at the top of this question is that these are 2 structural isomers. So what these tell me is that both of these guys have the same formula, but they have a different structure. So they're bonded differently. So I look at molecule number 2, I do the exact same thing. I'm looking at 1700. I'm looking at CH, and I'm using that as reference guidelines. I see that this one also has an OH. So both of these molecules are alcohols because I also see that there's no C double bond O. And again, it's an OR option for the achieved. It's an AND option to get to the merit, and you should be identifying that you have an alcohol. This bit is going to be the hardest if you're aiming for the achieve because those functional groups on the IR can be a little bit difficult to see. So you just got to get used to seeing the pattern. Once you see them, though, it's pretty straightforward. All right, so that was one of the achieve requirements here so that you can use the IR to identify things that are not there or not there, and I just need one correct identification. Second thing that we need to do is for the CMMR. Lots of different ways I can give you the achieve point for CMMR. The easiest way is just to count the number of lines you see there because that tells you carbon environment. So 1, 2, 3, 4, 5. There are 5 carbon environments. All right. There are 2 other ways that I can give an achieved for the CMMR, but it's probably unlikely you will use either of those 2. The first is that you have identified a carbon environment. So that means that you've used the resource sheet, which I now need to grab. And say, for example, you looked at it and you're like, ooh, I have a peak that's all the way over here around 60. And around 60, I should know that I should have OHs. So what you could do also for the achieved is identifying that this is a CO of some kind. So that's the other one. Again, it's an OR option. But most likely, you guys are just going to go by counting. That's the easier way to do it. The other thing is to state symmetry. You have a 50-50 chance of getting that right or wrong. You either say it is symmetrical or it isn't symmetrical. but you're going to have to do more working to figure that out. So it's unlikely if you're just scraping by for an achieved, you'll be doing that. On molecule number 2, CMMR, we see the same thing. 1, 2, 3, 4, 5 carbon environments. So what we can tell already looking at these 2 molecules is that they're very similar. Obviously, the same number of carbons because they're structural isomers. Both of them having alcohols because we can see that from the IR spectra. Right? Are we okay so far? Cool. So that will tick off the requirement here for the achieved. The last thing you need to do for an achieved is you need to do the mass spec, and you have to identify either the molecular ion or the base peak. I would say identify both just for the safety net. The one you're more likely to make a mistake on is the molecular ion because you might get confused and be like, ooh, is this tiny peak a molecular ion or not? Your best bet to make sure you get the achieved is labeling that base peak every single time, which is our 100%. So this here is my base peak. This here is my molecular ion. Again, it's going to be a nice little OR option to get either one of those, and you'll have enough for an achieved. So this is a very, very simple assessment to get the achieved on. Again, this one, molecular ion, has been labeled for you because it's too small. And then this one here is my 100%. So that's my base peak. Right, I'm not sure how far you guys have gotten, so I'm going to just check in with you guys. Have you figured out how many carbons are involved in this molecule? 5? All right, so you guys have figured out that there's 5 carbons, and I'll agree with you on that. Have you guys figured out anything about structure yet? No? All right, so I'm going to give you guys some time so you can take some guesses on what potential molecules these could be. Molecule 1 and molecule 2 are different molecules. You can see that from the mass spec. So play around with the 5 carbon alcohol and see if you can figure out what molecules could it be. Remember, if you don't have the right answer, that's okay because you can use that as the excellence to eliminate the isomer. So I'll give you guys a couple minutes to do that, and then we'll work through it some more. All right, let's talk about the answer to this question and how to bring this guy up to the merit level. So, are you ready? Yes? Hey, team, ready? Okay. So, first thing on the merit is that we need to make sure we use all the IR information, which we have. We stated that there's OH there, there's no carbonyl. We know that this is an alcohol. So we've done that before. Second thing we need to do for the merit is that I need to start seeing that you understand unique carbon environments and using your reference sheet. So we want the second page of that reference sheet. And what we're basically looking for is, can we find something that says OH? So we see that carbon attached to an OH is between 50 and 70. And I just want to double check that that is the case. So 50 to 70, this one here would be my COH. And that one is my, well, COH. So basically what I'm looking for at the merit level is that you have both of these. It's kind of like an and option. It's the best way I can describe it. You're just getting a little bit more information. Ooh, squish that in. All right. So last thing we need to do for the achieved is we need to use the mass spec and identify charge fragments. We can't do that until we've identified the molecule. So what I'm going to do is I'm going to list out some choices in molecules. And then I'll also talk about the excellence and how you'd be able to distinguish the two. A lot of you guys have molecules, so you're not sure which one ties to which spectrum. So I saw a lot of you guys write down I'm actually going to write this down in excellence because a lot of you guys showed me you eliminated it, was you wrote the 5 carbons down. 1, 2, 3, 4, 5. And then you put the OH in the center. As one of your possible answers. I saw that on a couple of people's pieces of paper, which is good. So a lot of people recognize once they put this one down that this was not one of our options. Why is this not? There's symmetry. So this is not one of the possible answers for question or molecule 1 or molecule 2 because we see that there's symmetry. And it has 3 carbon environments. So this one here is not the answer. For molecule, let's see, number 1 or number 2. Are we okay with that so far? All right. Then you guys had a little play with the OH. You started moving them around. The next answer I saw most of you guys have was that you moved the OH onto carbon number 2. One, two, three, four, 5. You moved the OH into carbon number 2. Go with that? Happy with that? Cool. Does this one meet the criteria? Yes. 5 carbon environments. This one does. Now, this one, we don't know at this point, is this the answer for for molecule 1 or for molecule 2? If you are aiming for a merit, you could stop here and not further justify it and be okay. The other option that a lot of you guys came up with is you move the OH down to carbon number 1. Oops, what am I doing? 1, 2, 3, 4, 5. So that is on carbon number 1. So a lot of you guys got down to these 3 as your choices. Both of these carbons are correct in a sense that they meet the requirements, but we do need to tie which molecule is for the spectrum number 1 and which one's for spectrum number 2. That's getting you towards the excellence level. One of the things one of the things you guys can start thinking about to help you figure out which molecule gets assigned to which spectra is looking at things like the fragments. So first off, if you guys remember from yesterday's lesson, Mondays, I talked a bit about clustering and how things that are clustering together like this suggest that there's a long carbon chain. Whereas if the cluster seems to get pulled apart, it suggests that there's something that's like interfering with that cluster of the carbon chain, potentially an alcohol that's on carbon 2 instead of on carbon 1. So this is a nice little cluster. This cluster of 4 has been interrupted by the OH. So that's one way you can start getting a hint which molecule ties with which one. The other thing to look at, which is going to be more accurate, is going to be your mass spec. And I just want to point out some things. I'm going to try to zoom out so we can see both of them at the same time. But what we'll notice when we're looking at these two guys is that the mass spec for these 2 molecules do not look the same, which is because since they are different molecules, they're going to fragment in different patterns. So what are some things that we notice? And I'm going to put this in orange pen so that way we're starting to kind of unpack and process. what do we notice about I think that's molecule number 1 versus molecule number 2, which is on the bottom. Sorry, yeah, molecule number 1 versus molecule number 2. What do we notice about this top one versus this bottom one? It has more lines. Where is the number for some of these base peaks? Because that tells me most common fragment. So base peak equals most common fragment, which is telling me how the molecule breaks. So when I'm looking at this guy, the base peak for my first molecule is at 41, 42, 43. I think 40, 41, 42. Is that right? Am I counting it correctly? 42. Whereas this one, is it 43? Am I just miscounting? 40, 41, 42. Yeah, 42. It's okay. All right, this one down here, when I'm looking at it, it's at 45. Yeah. This one also seems to have a nice big peak at 55. I'm just making notes of where I see things, so that way when I break up my molecule, I can get kind of trends and patterns. This one here, 71, 2, 3, 4. That's a 71, 2, 3. I'm just having a look-see at what I see that's kind of big and noticeable. 1, 2, 3. So you see, I'm just going through and I'm just noting some more obvious peaks just to see if I can maybe use them to help me figure out what's going on with that molecule. So that's the bottom one. On this guy here, we have a lot more options. So I'm just going to label a couple of them. This one here I see is 31. There's a nice big one here at 55. There's another one at 70. You can see another one at 41. I can see another one at 29. There's a lot of options for me. I think that's, what is that? 27 is an option, maybe, if something going on. 43 is an option. 57 is an option. So I'm just going through and I'm just putting some numbers down, because when I break up my molecule, I want to see if there's any sort of trends and patterns when I'm looking at it. Are we good so far? All right. So I'm just taking this guy over here, and what I'm going to do is I'm going to start breaking things up so I can see if there's anything that's unique to that molecule if it fragments, and if I can see, what would be a common fragment. So those are the two things we're thinking about. And let me write that down in another color. What fragmentations are unique and what fragmentation is more common? Better? Okay. So those are the two things that I'm asking when I look at how I break things up. Are we okay with that so far? And the fact of where that OH is will influence then what is possible to break. So one of the first things that I noticed that is unique to to the bottom structure here with the alcohol and carbon number 1 is that it is possible for it to have a chain of 4 carbons. With this guy here, there is no way of it to have a chain of 4 carbons with the CH2, 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 CH3. Because if I was trying to do that, it would only end up being CH to the CH2. So what you're going to be doing when you're looking at this is you're going to be breaking up the molecule and you're going to be seeing what various masses do we have. So if I break it up here, and I count how much I have there, I would have 14 plus 14 plus 14 plus 13. So that gives me a total of 57. So that would tell me that there should be a unique peak there that I wouldn't be able to see on the other one. This section here with the alcohol, if I added up the mass of the oxygen, the hydrogen, the carbon, that would be 31. So what that tells me is that this guy over here, I could see possible peaks at 31 and 57 for the fragmentation. I wouldn't be able to do that for this guy up here. So we can start looking at them. Do I see something that has a 30? I do see a 31, and I do see a 57 on this guy. Do I see a 31 and a 57 on this guy? No. So you see how that kind of helps me figure out which one's which. Yeah? The other thing to ask yourself is what fragments are more common. So when we think about our fragmentation process, this fragmentation process commonly happens at the functional group. That's where the molecule is least stable. So like, for example, if I was looking at this guy up here, it would probably break somewhere with the OH. So it could break with the CH3s over here, like that, and then this OH with the 2 carbons here. If it did that, I would expect a peak at 45. I would also expect a peak at 43 as a common one. So again, we can have a look. Do we see things that are like 43, 45? We see that this guy's base peak is actually 45, right? So that kind of, again, ties into what I'm looking at fragment-wise and what things are probably lining up to be. I also see that there was a 43 peak, that guy over there. So you see how it's going to match up? And you can have a little play with it to kind of verify it, but that would be enough to verify that this bottom one is for molecule number 1. And the top one is molecule number 2. So that's why that fragmentation is really important. It can help us distinguish what's what. All right, keep going. Clean up our answers, just make sure we get our excellence. Okay. Well, actually, our merit and our excellence. So for the merit, what I'm looking for is you have identified any fragment, and it could be anything on the spectra. So for this guy here with molecule number 1, we talked about how it could break and you'd have a fragment at 31. I could say, okay, 31, my fragment is CH2OH, and I need to put a little plus sign to indicate that that's that fragment. So that's something I need to do for the merit. Huh? That's molecule number 1. So right now, if I have done this for molecule number 1, I would be at the merit level. I've identified what molecule it is, and I've identified one of the fragments from that molecule. We good? Keep going. All right, for molecule number 2, let's say I want to figure out another one of my fragments. It doesn't need to be the base peak, but I'm going to choose the base peak because it's an easy one to do because I've already figured it out here. So I would go, oh, this peak over here is CH3 CH3OH, and I'll put the positive sign to represent that that's my 45. So again, figured out the molecule, figured out one of the fragments. Looking at our success criteria, we are now at the merit level. So I'm looking at this guy over here. So I've done the mass spec, I've identified a charged particle, and I've identified the molecule. Gets me up to merit. Right, excellence criteria is we need to integrate our spectra together. We also need to show what was lost, so the uncharged fragments, and we need to show an elimination of a possible isomer. So let me show you what I mean by that. So the first thing is, what is the uncharged fragment? This is what is being read on the mass spec. Remember, mass spec can only read the charged fragments. So I am indicating what has been lost. So the lost bit is the second half of the molecule, which will add it up to the molecule. So that's going to be that CH2, CH2, CH3. And I indicate that that's the uncharged fragment with the dot. So this is on molecule number 2. Cool. Keep going. All right, this one over here. In this case, what I've lost is my 4-carbon chain, CH2, 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 CH3 with a dot. Oh, sorry, it's out of focus. So that's on molecule number 1. So starting to get up to that excellence level. All right, keep going. Yeah, okay. Last thing I need to do is integrate my spectra together. So for molecule number 1, I can show that, actually I should put the arrow going that way. So this confirms alcohol. This one over here, if I wanted to link these two spectra together, I would say that we've, the mass means that there are 5 carbons, and these two match. So this says no symmetry. So you see how I'm starting to integrate my spectra together, because the numbers match. So this one's 5 carbon environments. This has 5 carbons in the mass. Cool. And then you'd be doing the same thing on the other one. You do it. So this here confirms OH. Mass means there are 5 carbons. These two, the numbers match. Therefore, no symmetry. Did I write no symmetry? Yeah, no symmetry. Cool. All right. So if you're aiming for an excellence, the other thing is to eliminate other molecules. This is an example of one of the molecules being eliminated. If you wrote these two down as possible answers and you're at the excellence level, you'll be able to figure out which one it is based off of the fragment pattern. If you were only aiming for merit, you would have given me one of these two answers, but you wouldn't have told me why the other one isn't the right answer. So you could be using the fragments as your justification. I ideally want at least 2 eliminations just to see that you guys know what the rule is and why. You could always write down another organic molecule and eliminate it for whatever reason you want. So in this case, you're working through based on the fragments as your elimination, but you could also just give me another molecule that has some symmetry that you would eliminate because it has fewer carbon environments. Or you could just show me elimination because you know it's not a certain functional group. Cool. Right, questions, concerns, comments? Yes. On the which one? The 7. So I used the resource sheet, and you see how this has approximate values for chemical shifts in the CMMR spectra. I look for the OH, and it says it's between 50 and 70. And then when I look on here, that is between 50 and 70. Yeah? It's just a way to confirm yourself. All right. Let me just switch back to trying to see. We end at 40. Okay. Just so you guys are aware of our deadlines. I don't see you guys on Monday because it's King's birthday. So I see you guys on Thursday and Friday. We have quite a bit of time between now and Thursday that I think you guys can do some practice at home. And I think we can do the first attempt for the spec on Thursday if you guys feel like okay with it. Or do you guys feel like you need another day in class practicing with me? Another day in class? What do you guys feel on the side? You're okay? What about? So you want me to shift the first attempt to Friday next week? Yeah, I don't mind shifting everything by a day. Okay, so that's what we'll do. We will shift the practice, the first attempt of the spec internal to the Friday. It's basically like a practice, because if you guys remember, what I like to do is give you guys the best grade out of, like, there's going to be 4 questions total. I'll give you 2 on the Friday next week as your first attempt, and then you guys will get the feedback on the Monday. And then I'll give you the feedback on the Monday, and then I'll give you guys your second attempt on the Thursday. Does that sound good? Okay. That'll be Thursday, June. Help me. What is that day? June 15th. Cool. I'm taking the best 2 out of the 4. If you do really well in the first 2 questions on the Friday, then you can be done. If you get like an excellence on one and a merit on the other one, then when you take the second attempt, you only need 1 more excellence to get excellence overall. Cool. All right, feel free to have some practice. You guys have 10 minutes left. Do you guys want to use preferred activity time at all today? Or you just want to save it? Save it? All right, cool. So you're up to 90 minutes now. All right, cool. Got some work done.